as I had emailed everyone, there the problem set is available. Done it already. Anyway, we'll have our problem session as always. And then there will be one more assignment that will be distributed on Tuesday, the 25th, and then due on Friday, the 5th at 5 o'clock in the afternoon. So we'll have time to talk about it. I will be gone all of next week, so there won't be lecture next week. But we'll have a makeup on the Wednesday after Thanksgiving. Okay? All right.
Do you know what time in the evening?
Well, the last time everyone was available when we had the exam, from 5 to 7.
Oh, okay. All right.
So that's the time I assumed people would be available again. All right. We've been talking about angular momentum in quantum mechanics, a very important problem. And we are looking at representations. So we have the eigenstates, the simultaneous eigenstates of the magnitude squared of angular momentum and one projection, the standard basis. We chose that, we call that direction the z direction. Okay? And we can look at matrix representations of that, those of the components of angular momentum and the magnitude squared of angular momentum in the standard basis. Okay? So clearly these operators are diagonal in that basis. They're diagonal matrices. Those are the matrix elements. And then to get the other components, the x and y components, we appeal to the raising and lowering operators, the relationship between the x and y components of angular momentum and the raising and lowering operators. So the raising and lowering operators are not diagonal in this basis, but they're block diagonal, meaning that they don't connect states with different magnitude of angular momentum. They connect states with different projection for a fixed magnitude, right? So, and they only have non-zero matrix elements, one off of the diagonal, m plus or minus 1. We typically then look at, we rarely would write down the matrix representation for all j. Since they're block diagonal, we restrict our attention to each block associated with the given magnitude eigenvalue j. Okay? So for j equals a half, these are the matrix representations for the three components of angular momentum. Obviously, jz is diagonal, it always is, and jx and jy have non-zero elements, one off the diagonal. And of course, these components of angular momentum are related to the familiar Pauli operators that we discussed at the very beginning of the semester and that we will return to after Thanksgiving. J equals 1, here are the matrix representations. Again, jz is diagonal, and this is j plus. Once we have j plus, then we can get j minus by just taking the adjoint. And then once we have the adjoint, we can get the Hermitian and anti-Hermitian parts of that. Okay? and et cetera, et cetera. So when j is an integer, there are representations that are associated with orbital angular momentum, the motion of particles in higher dimensional space than 1. And as we discussed, the states then live in a Hilbert space, which is the space of square normalizable functions on the sphere. So the position representation now of our eigenvectors of angular momentum are, of course, the familiar spherical harmonics. They form a complete set of functions on the sphere. They're orthonormal functions. That is to say, they are complete in the sense that they form a resolution of the identity on this space, and that is expressible in position representation, that when you sum over all these angular momentums, you get a delta function on the sphere. They are orthonormal, meaning that when you integrate two of them relative to one another, conjugating one on the sphere, that inner product is 0 unless L equals L prime and N equals N prime, right? And any function on the sphere, which can be written abstractly as some ket in this Hilbert space, can be expanded as a superposition of the spherical harmonics. And that is a kind of general Fourier series, if you like. It's a usual kind of expansion in orthogonal functions, but these are orthogonal functions on the sphere. All right? What we were talking about at the end of the lecture was what these functions are and their relation to what we call the solid harmonics, or sometimes known as the spherical tensors. We'll talk a lot about spherical tensors next semester, but let's just say a few words here. Oh, I guess let me just first say a few, again, remind you of some relations of the properties of spherical harmonics. First of all, they are eigenstates of parity. As they must be, because angular momentum vector is invariant under reflection. Because x goes to minus x, and p goes to minus p, and angular momentum is x cross p. So the angular momentum vector is invariant under, that's why it's sometimes called a pseudo-vector rather than the vector, because most vectors go to minus that if you reflect. But the angular momentum stays the same. So they're eigenstates of parity. A parity transformation just says that theta goes to theta plus pi. And under that, the YLM, under the parity transformation, is an eigenstate, and the eigenvalue is plus or minus 1. And it's plus 1 for the even L, and it's minus 1 for the odd L. Okay? We also have property that if you conjugate it, that's the same thing as y with minus n, and then minus 1. Get that out there. Okay? The other thing that again, I wanted to emphasize was these things I called y, l, m as a function of the position vector, which I defined as r to the l. It's a function of three-dimensional space. Okay? And these things I call the solid harmonics. That's a kind of old-fashioned term. I'm an old-fashioned guy. Or they're sometimes called the spherical tensors. Actually, the irreducible spherical tensors. And these functions can also, so let's write them down. Y0, 0 is 1 over pi. Y1, 0 is equal to square root of 3 over 4 pi r cos theta, which is that, and y1 plus or minus 1 is 3 over 8 pi r sine theta e plus or minus I, and there's a minus plus out there, and that's minus plus the square root of 3 over 4 pi x plus or minus I y over root 2. And we can go on from there. For example, this is some factor r squared sine squared, not squared, cos squared. R squared sine squared theta e plus or minus I 2 pi, which is some factor plus or minus x plus or minus iy over root 2 squared. And y2, 1 is some factor r sine theta cos phi e to the plus or minus I phi, some factor times plus or minus x plus or minus iy over root 2 times z, etc. So, yeah.
Are you thinking about those as projections as you write them? Like I noticed you were thinking about r squared, sine squared theta, or
So,
just how do you remember those?
okay, yeah, so that's how I'm going to explain that, where that's how the hell do I remember that,
Okay.
and how will you remember that. So, what we see here is that these functions are I can think about them as polynomials in 3 variables: x plus, x minus, and z. Okay? So we have spherical coordinates r theta phi. And then we have something we call the spherical basis. Which are components with respect to these complex vectors. Okay? So, as we discussed early in the semester, these vectors are eigenstates of rotation in 3D about the z-axis. So if I rotate these vectors about the z-axis, They come back to themselves up to an overall eigenvalue. So if I rotate this by an angle phi about the z-axis on these vectors we call EQ, where Q takes on the values +1, 0, and -1. Okay? That this vector comes back to itself with a phase factor. So if I rotate these vectors about the z-axis, well, obviously this stays the same. You rotate the z-axis, and that's q0, so that's an eigenvector with eigenvalue 1. If I rotate this, of course, x goes into y, and y goes into x, but exactly in the right way, such that it still stays the same, but it picks up just an overall phase. Okay? And because these vectors are eigenvectors of rotation in three-dimensional space about the z-axis, they play a special role in terms of the eigenfunctions of angular momentum. Because the eigenfunctions of angular momentum about with choosing the standard basis are eigenfunctions of rotation about the z-axis. So polynomials in the components, this is the component along E plus, this is the component along E minus, this is the component along E0. Polynomials in that can be, in the right way, are eigenstates of rotations about the z-axis. Okay? So, well, this is just a scalar, so it doesn't, it's a eigenstate of rotation on any axis, just a number. And it's 1 over 4 pi is just so that when you square it and you integrate over the sphere, and there are 4 pi steradians, then you get 1. The three components L equals 1 are really just the same thing as three-dimensional space, because there are 2L plus 1 means 3 different eigenvectors. So there's an intimate relationship between L equals 1 and three-dimensional space. That's why the photon has spin 1. Because the photon is a vector in three-dimensional space. So it's got spin 1. All right, a little side there. Right, so these are just, now why do I just remember that? There's no way to remember that 3, and that's why I don't remember these, so there's something else, 16 pi. This I just remember. But you don't have to. But you should remember this. Okay, so these are just the components along E plus, E minus, and 0. Now this horrible factor out there, minus plus, why is that there? Well, that's just there because you want this to have the right conventions for the spherical harmonics. Okay, so that the component along E plus is y1 plus 1, etc. So these are the components there. It's the maximum projection of angular momentum. And then with 0 projection, well, that's E0. Okay, so that's Z. And then we go from there. What is generally true is that YL n equals L, or plus or minus L. That's the stretch state, the state with the maximum or the minimum projection of angular momentum. That is some factor times plus or minus x plus or minus IY over 2 to the power L. And we can get that if we like. Well, if that's the only polynomial that will have that much angular momentum. Each one has 1 unit, and this has L of them, right? Because this was either the plus this is like e to the plus, this is e to the, this is r, e to the plus or minus I phi in spherical coordinates. That's what that combination is.
And the sine theta?
Yes, excuse me, sine theta, thank you. Oh, x, yeah, the sine theta, that's there. But I wanted to emphasize that because when you multiply this to the power L, you get plus or minus I L phi. And we remember that e to the plus or minus m phi, or whatever m is, that this is an eigenvector of Lz with eigenvalue L. So if I'm going to have m equals L, I got to have, that's the only way I can do it. And then I can apply the lowering operator. And the lowering operator, it's going to take this down to plus or minus x plus or minus I y to the L minus 1 times z. And then, now where the heck is the lowering operator here? We had the lowering operator in matrix form, but now we need the lowering operator in the position representation, right? So let me just find what I was looking for here. Right, okay, so the components of angular momentum operator in position representation. Right? So, well, LZ is, remember position, what we're talking about here is orbital angular momentum. L is R cross P. Right?
That's a quick question.
Yes, please.
So the x, y, and z, like I'm trying to figure out, do those point in the direction then of L, or I'm just trying to figure out?
No, they do
it's
not.
It's just more abstract? And
No, what I would say is the following. Remember what the YLMs are. The YLMs represent probability distributions for particles to be located with a certain direction in space. So we're talking about particles moving three-dimensional space, and we know there's a position eigenvector. It could be at a certain distance from the origin and some polar angles, right? So the YLMs are telling me in context of quantum mechanics of what is the probability amplitude. The square is the probability density for the particle to be, you know, in a certain direction with a certain solid angle. Okay? So given that, we're looking for the distributions that are eigenstates of rotation, such that if you rotate the whole distribution, it comes back to itself up to a whole phase. I'm going to talk more about this connection to orbits a little bit later in the lecture. So let's come back to this because there is an abstraction here, but there is physics too. Okay? Not that physics isn't abstract, but it's not just math. Okay, so yeah, let's put it on. Let's just write it. LZ is x py minus y dx, right? That's what it is. These are all operators. Keep changing this call. Right? And in spherical coordinates, we showed that this was h bar over I, respect to, that's what we found. But I can also write it in terms of the spherical basis. The component's derivatives with respect to the spherical basis, x plus, x minus, and z. If you go through that, you find this.
What was X plus?
No, that's wrong. That's X minus. That's what you should find. And then these guys, we can write the following. L plus, which is Lx plus Ly over 2. Writing L plus Lx, and now Lx, of course, is Z P Y minus Y P Z.
Is there an ILY?
Yes, indeed, thank you. That this is equal to root 2 x plus d by dz plus z d by dx minus. Right, and then L minus is the adjunct. So you could take those operators, there should be H bars in there. In fact, let's just write this. Get rid of the H bars. For example, I take this operator and I apply it to this. What you see is I take one derivative of x plus and I multiply it by z. And I can keep doing that. So if I were trapped on a desert island and I wanted to figure out, I had nothing else to do, I was in solitary confinement, I could figure out all the YLMs, keep myself occupied. You know, some people would talk to Wilson the soccer ball, I had to figure out the YLMs.
It was volleyball.
It was a volleyball?
Yeah.
Okay.
I thought it was a football. It's a volleyball.
No, I thought it was a soccer ball.
No, Wilson was the name of the brand of the
Yeah.
volleyball.
Okay. So, pick your poison. Okay. Right. So, you should always keep this in mind. I never, ever think about the spherical harmonics in terms of sine thetas and cosine thetas, and I always think about the spherical harmonics this way. Because it's really, you'll understand what this is about. Multiplications. Otherwise, where do these things come? All right. Now, I wanted to just say just a few words, and this kind of follows on to your question of how do I think about this, you know, is it the direction of angular momentum and so forth. Remember, so I want to, let me maybe just see the next thing I should do just to motivate this is, let me just show a picture. Oh, I gotta get this stupid remote over there. I can't remember what that movie is called.
Really?
The one with the volleyball and/or soccer.
Custom.
Yeah, that's right.
I thought it was Mr. Wilson and his flying circus. We were talking more about Wilson.
The football.
So, you've all seen little graphics of what when we wants to sort of plot the spherical harmonics. Let me show those pictures again and explain to you some important points in the relationship to the physics. Does it work? Right. So, let me shrink this. So what's being plotted here is two things. These are the squares of the circle harmonics. You know, I stole this from some other website, so they have their own notation here. Y0, 0, Y1, 0, Y1, 1, etc. Plotted as the square, okay? Now notice that they're all azimuthally symmetric. The squares must be, because they're eigenstates of rotation around the z-axis. The vector, the circle harmonic itself is generally a complex function, right? Let me come back to the other, and just let's put back on the lights over here. And let's just come over here. It's going to see, right? So here are the solid harmonics. Okay, so what's being plotted there is as a polar plot. This either in that red one on the left, what's being plotted is the square of YLN as a function of theta and phi, as a polar plot. Okay, so the length of that vector is related to what this number is. That's what's being plotted. So if this is 0, then right in the middle, it's 0. As I go to bigger, if I go up to a larger theta, if I go up to theta equals 0, then it's a maximum value. Okay? So that's looking as a function of theta as cosine squared. This guy, as a function of theta, is looking like sine squared. So, let me again come back.
It is sine squared.
Yeah, it is. And so it looks like it. Exactly what it is. Okay, so how do we think about this physically? What the heck do those shapes mean in terms of angular momentum? Well, so remember, when we're talking about, we'll come over here. We get this board over here. We have this angular momentum, right? So a particle that has angular momentum has to have some lever arm from the origin and some momentum perpendicular to that lever arm. So for example, if here's three-dimensional space, x, y, z, if I want to have zero angular momentum along the z-axis, I cannot have my orbit be in the xy plane. If my orbit is in the xy plane, well, then I have a lot of angular momentum along z. So it better be the case that if I have zero projection, if I look at the case where m equals 0, that's the case that has zero projection along the angular momentum. It can't have any probability amplitude for the particle to have theta equals, I can't have theta equals pi. This is my position vector. If my position vector is pi, if my particle is somewhere in the xy plane, it would have a lot of angular momentum along the z-axis. Pi over 2. I don't know why my brain's not completely firing today. Right? And if the particle was oscillating in, say, the y-z plane, if it had that kind of orbit, well, then it would have all of its angular momentum along, in this case, the x-axis, and have none along the z-axis. Now, of course, it can't just have that orbit because it's got to be rotationally invariant. So it's something that's kind of like this, but I don't know where it is around the z-axis. And that's what that is. This guy, which is the y10, has 0 probability amplitude to be at theta equals pi over 2. Because if it was at theta equals pi over 2, it would have a lot of angular momentum along the z-axis. And it has its maximum probability amplitude to be at theta equals 0. Because if it's at theta equals 0, it's oscillating in somewhere in the xz or yz or some, and it's all rotationally symmetric. In contrast, if I have angular momentum with projection plus or minus 1, well, that's, you know, the thing that has its angular momentum along either the x-axis or the y-axis in some combination, and it's the opposite. It's got 0 probability amplitude at theta equals 0 and maximum probability amplitude at theta equals pi over 2. So these things mean something in terms of angular momentum. They're not just, you know, oh God, what the hell do these orbitals have to do with angular momentum? They have to do with the motion particles and their probability amplitude. Yeah?
So, if particles in one of these states, would it have a unit probability of being on the surface, or is there like some fuzziness around it?
This is a plot of the wave function squared.
Okay.
So this is telling me the probability amplitude to be in a certain, so let's look at this guy. So if I'm in this little patch, let me write this down. So you see this YLN of theta and pi squared, what is that? That is if I'm so here I am on the sphere. I'm some distance from the origin, I'm not saying what that is, but I'm in a little, somewhere in a little patch, a differential solid angle, and this is some theta and some phi. And this number represents the probability that I will find the particle in that little patch on the sky. So it says if I, you know, I'm sort of, you know, looking at a galaxy far, far away, and I want to know, I'm at some polar angles, there's some probability that the photons say I will detect it in that patch. So if I'm looking relative to, you know, how it's spinning, right on the axis of the spinning, then I have a high probability of finding the particle. If I'm looking at 90 degrees relative to that spin, then I have no probability. So this is the length of the you know, if I think, I can't reach because I'm too shorty. You know, the length of this is representing this. So it has big probability here, little probability there. Okay. Yeah.
So if you're talking about like real atoms and stuff like that,
As opposed to fake atoms.
yeah, I mean, yeah.
If we apply this to the case of atoms. Yeah.
Okay. Are, I guess, like all the atoms that have random z-axis or something, like what their axis that we label as z will be different for all different atoms unless we do a field of some sort to align them.
So this is representing, as you all know, of course, and we're going to talk about that. Well, so some of that today, and we'll, you know, really go into depth next semester. Talk about the application in atomic physics. You know, these would represent, you know, atomic orbitals, right? So say the ground state of hydrogen, it's the angular distribution of where the electron is relative to the nucleus is this, right? Because it's an L equals 0 state. So in that case, what that says is that it's completely uncertain what its direction is, right? The states that are, have, some finite projection along some quantization axis have this distribution of probability distribution. Now, if I understand your question correctly, and you'll elaborate if you don't, what the heck is the z-axis of the atom? And the answer is, there is none. So, unless we break the degeneracy somehow and define some special direction, like we put the atom inside a magnetic field, which is pointing in a certain direction, or between capacitor plates, which have electric fields, then there is no direction. The atom isn't necessarily, has a well-defined, and it can be in a superposition of any of the YLMs for different M's, and have the same energy, because they're all degenerate. It's only when you break that degeneracy that you can force the atom to have a well-defined projection of angular momentum along a certain direction.
So I mean, it's kind of like, I hate to use the word projective measurement, but if you were trying to find the electron and you were trying to project it on the z-axis,
well, so you can prepare the atoms in a state with a definite projective angular momentum in the way that you just described. If I had some kind of apparatus that was able to, in some sense, ask the atom, had a quantization axis that said, are you along the z-axis with this magnetic momentum, then yes, post-measurement we would have projected it. But the way we often do it, and in Professor Becerra's lab, it's been done all the time, it is what we call optical pumping. So you can cool the atoms into a state with a well-defined projective angular momentum if you put those atoms in a magnetic field which distinguishes those different projections of angular momentum, and then you use the angular momentum of light to push it, cool it, spin cool it. We'll talk about that next semester. Okay, now there's this other picture here, and I also wanted to say a few words about that as well. Now, of course, these are the squares of the amplitudes. The amplitudes themselves are complex numbers, right? So, here it is as a function of theta, or if I put the r in here as a function of z. Notice that this guy is, if we sketch this guy out as a polar plot, it's at theta equals 0, it's the maximum, and then it goes like cosine beta. This is, the orbital here. Okay, so this is the z-axis, and this is theta. And the length of this vector is cosine. This is 1, this is 0. Okay, that's what those orbitals are. Now, of course, up here, cosine is plus, and down here it's minus. So the orbital is anisymmetric, as it must be, right? And that's because, in space, the guy is, if it's going like this, it's up here, it's either going to the right or the left. It's anisymmetric that way. Now, these guys are complex, so it's hard to draw them. But often, especially the physical chemists, will not look at these guys, but the real and imaginary parts. Okay? So I can define another set of tensors. they have a name. It's not something we do often in physics, but I want to make a connection because we will. Um, Oh, you stupid thing. I hate you. Yeah, screw it. Let me just define, I'm not going to give them a name. I'm just going to tell you what I'm talking about. So let's talk about in the real and imaginary parts here. So in this case, that would be something along x and something along y. And then the other ones will be, you know, some crazy combinations of x squareds and z squareds and so forth. These things are called, from my perspective, they're called the irreducible Cartesian tensors, as opposed to the irreducible spherical tensors. And that is what's being drawn here. So you'll often see these. So this is y0, 0. This is the YL0 projections are the same, right? Because those were always real. But then these guys, you notice what they look like, and the blue is positive and the gold is negative in this picture. I mean, these orbitals are exactly, they're just the rotations of the ones that, you know, that little figure eight thing I drew. This was the figure eight along the x-axis, I mean the z-axis. This is the figure eight along the x-axis, and this is the figure eight along the y-axis. So sometimes these are called, you know, well, let me remind you of one other thing. Remember this arcane notation that we have about orbitals. S orbitals, p orbitals, d orbitals. They come from a late 19th century spectroscopy where there was the sharp spectrum, the principal spectrum, the diffuse spectrum, the fine spectrum, and then they ran out of English to GHIJK. We still call them that. So this is the S orbital. S means L equals 0. These are the p orbitals. The p orbitals, this is sometimes called the pz, the px, and the py. Right? Because they are the components, they really are just, but they have the right angular component. You know, this is the x, I mean, this is the z, this is x and y. And then these are more complicated. This is 3z squared minus r squared, and then there's x times y and y times x, et cetera, et cetera.
So these aren't probability amplitudes, I mean the distributions?
These are the probability amplitudes.
Okay, so they really don't have a physical meaning, do they? Okay.
I don't know what you mean by a physical meaning.
Isn't it the distribution that we really care about? We can't really measure the amplitude or something?
Oh, yes,
Isn't it?
but I mean, but you know, it's true that ultimately if I did a measurement, so if the particle was in an one of these Engelmann eigenstates, and I did a measurement, and I want to know what's the probability to find it in that little solid angle, then it's only the square that matters.
Is
You're
that
correct.
about the chemists somehow?
No, but, we care about superpositions. So suppose I was in a superposition of this and this. Well then, what I would find is that the particle would have more probability amplitude at theta equals 0 because I would add, I'd have constructive interference between these two, and I'd have less probability amplitude at theta equals pi. In fact, if I want to make an electric dipole moment, then I have to have a superposition of s and p orbitals. So the amplitude, the sign matters. The fact that these things are not just all, positive matters in superposition. So that's physical. Yeah.
So you were saying, so if I understood correctly, you're saying that these are showing the probability amplitudes, but the green, I'm sorry, the two different colors are,
Two signs.
yes.
Plus or minus.
Okay, like the what kind of relative phase, or no?
Well, I mean, it's just the value of it's the value of the amplitude at that theta and phi.
The value of the probability amplitude?
That's correct.
So it could be negative though, or?
Sure, probability amplitudes can be complex.
Okay, I guess I'm thinking of probability amplitude being the absolute square, but no,
No,
it's
that's
just
the probability.
the probability. You're just talking about the complex. Okay,
So,
okay.
so this is just a language, this is a semantic point.
Okay.
Psi is the probability amplitude. Psi squared is the probability.
Okay.
Probability density. Okay? When we talk about probability amplitudes, we're talking about complex numbers, right? And now, it just turns out that, as I said, I can make them real,
Okay.
right, by this combination. And then they're just either real positive numbers or real negative numbers. But by choosing the Cartesian tensors, I can make them real. Generally, they're complex amplitudes, right? With that, I couldn't draw. But I can still, I can have a superposition of this and this. In fact, this guy represents, as we discussed, a particle moving around in a circle. It's a superposition of x motion and y motion. All right. Very good. All right, so get quite where I wanted to get, but that's okay, because I think it's useful to really emphasize what this physics is all about. All right, so we have these eigenstates of angular momentum, both for spin and orbit. I don't know what's with my ship today. Excuse me. So where we came from this, I want to return where this detour came from. We've been talking about quantum mechanics of motion in space for r and n greater than 1. Okay? So we're talking about motion of a particle in a plane or motion of a particle in three-dimensional space. Okay? And one of the things, so we want to return to this problem. I want to just remind us of a few things. First of all, about the classical description. So let's go back to thinking about where we were. Let's talk about the 2D isotropic okay? Where we were some lectures ago. So here we are in the xy plane. And generally, the particle is undergoing some kind of orbit, depending on whatever its initial conditions are, right? So there's some position as a function of time. Now, as we have discussed before, if we want to specify what that orbit is, we want to find the motion of the particle in the potential, simple mechanics, it's not enough just to specify the energy. There are many different orbits, all of which have the same energy. So, for example, if you're along the x and y axis, I could be oscillating with that amplitude back and forth with frequency omega, and that has exactly the same energy as going back and forth along the y-axis. And that if I have any intermediate amount of x and y, if I can go back and forth to the same amplitude along the diagonal. All of those have the same energy. And moreover, if I, depending on my initial conditions, if I start with a certain amount of amplitude along x and a certain amount of amplitude along y, depending upon what my initial momentum is, I could have something going around in a circle, which has exactly the same amount of energy as this. So the energy alone does not specify the orbit. I need to specify more. By the way, what is the angular momentum associated with these different orbits? Does this guy have any angular momentum? If the particle is oscillating along the x-axis? No. I mean, this is angular momentum, right? And, you know, x, if either x or y, if there's a place where x and y is both 0, then the angular momentum is 0. These have no angular momentum, but this has angular momentum. Okay? So to specify, generally speaking, we can say the following. In the classical description, in 1D, specifying the energy plus initial conditions, that gives me the whole orbit. Higher dimensions, I need more. Now, how, generally speaking, it's not clear that I'll be able to specify the orbit at all. Sometimes the motion is chaotic, classically, right? And yes, we could write down the equations of motion, but we could never integrate them very accurately for too long a time. However, there are some special cases where we can, for sure, where the system is integrable. If there are symmetries. Okay? So, for example, the 2D isotropic simple harmonic oscillator, we have rotational symmetry. Around the z-axis, right? And because of that, that meant that this was a central force, which meant that the component of LZ is conserved. So as we've said, emphasized many times, there's an intimate relationship between symmetry and conservation laws. Okay? So what that means in this case is that I can specify, because I have 2 degrees of freedom, I can nail down the orbit, what this orbit is going to be, by specifying 2 conserved quantities. In that case, so specify the orbit by the energy and the z component angle. Yeah,
The potential has rotational symmetry, but not the orbit, is that right?
that's correct.
Okay, thanks.
That's correct. And of course, the kinetic energy always has rotational symmetry. So as you say, it's all about the potential at that point. So if I specify the energy and the angular momentum, I specify the orbit. Okay. So these are, I also, and the initial conditions. So if I have this special case, then it's definitely I can find the orbit. It's regular motion, it's not chaotic. And there's a whole formalism about this in classical mechanics, which says generally, given n degrees of freedom, okay, for a Hamiltonian system, meaning it's conserved, there's energy is conserved. This is not friction, it's Hamiltonian dynamics. If there are n-1 constants of the motion or conserved quantity, then the system is integrable. Okay? And the way we can specify that orbit is through a set of canonical coordinates that are known as action angle variables. I don't know if you've studied that in your classical mechanics, but you could do it. So I could specify, a set of canonical coordinates, as we're going to call the actions, and conjugate momenta, which are angles. No, it's the other way around. These are the angles. These are the actions. So there's a formal description of this in classical mechanics. We've seen an example of this in simple harmonic oscillator. If this was Q and this was P, I can specify the orbit by the action, which is the radius of this amplitude, and the angle. So that if I specify what the action is, which is to say what the energy is in this case, and the angle, that's a set of canonical coordinates that specify the orbit. The actions are conserved. These are the n conserved quantities. One of them is energy. In this case, if there's a 1 degree of freedom, I just need 1 conserved quantity, it's the energy. And then the angle tells me where I am on the orbit. Okay? All right. So, make sure I don't leave something out. Right. All right, so that was 2D. Let's talk about 3R3. And let's talk about the case where I have, all right, so I'm moving in 3D space, as there's some trajectory here of particle. Okay, here's the origin. Here's the position vector. Okay. The particle has, along the radial direction, this particle has some momentum. So it's got some momentum over here, tangential to the trajectory. And it has a component, a radial component, and a tangential component. Now, if in this case, if we have the force, if we have a central force, then the potential is only a function of the distance from the origin, right? There's no torques in that case. Angular momentum is conserved. All right, let's now express the Hamiltonian in terms of this geometry. So my Hamiltonian is p squared over 2m plus the potential. Okay. And this is equal to the radial momentum and the tangential momentum. Right? Just having broken up the momentum into the components. Now, of course, the tangential momentum is related to the angular momentum, right? Because angular momentum L is position cross momentum. And that's the radial distance, the magnitude of this, times the lever arm. Right? So that means that P tangential squared is the magnitude of angular momentum squared over r squared. So that tells me that the Hamiltonian can be written as radial momentum, or radial kinetic energy, angular kinetic energy, which has the form of angular momentum squared over 2mr squared, and the potential. Familiar, I hope. Now, if I have a central potential, then, as we said, the potential is only a function of r. So, what can we say in this case? Well, if we have such a situation, this is always integrable in the way that I described. Why? What are the constants of motion that are obvious in this case? Well, we always have we have 3 degrees of freedom, and if we have 3 conserved quantities, then we're done. Those are the actions and the rest of the angles, and we're done. So what are the 3 conserved quantities in this case? Energy is good. Angular momentum, in fact, the magnitude of angular momentum. And any projection is also considered. The reason is this is rotationally symmetric. It doesn't depend on the direction in space. It just depends on the distance from the origin. And because I have rotational symmetric potential, not only is the magnitude of angular momentum conserved, but any component is also conserved. So LZ. So I can specify the orbit by specifying these three conserved quantities and what the initial condition is. I mean, you know that from Kepler's, your study of Kepler's motion, if you go back and review that kind of thing, right? If I tell you what the energy is and what the angular momentum is and what the projection is, then you know which ellipse the particle, the planet goes around the sun. Now, because of this, what we can see here is that we can write this in a Hamiltonian in terms of an effective potential for a given value of L. Right? Because my effective potential for a given value of L is just L squared over 2m r squared plus the potential. So, in order to find the orbit of the particle moving in three-dimensional space, I could just solve for its radial motion from the origin sitting in this potential, right? So if let's say we have the true potential as a function of the radial distance, look like that, for example. All right? Well, then the effective potential depends on adding in this term, which goes like 1 over r squared. And you have an additional potential, which is what is called the angular momentum barrier. So the total potential will be the sum of these potentials. If the angular momentum is 0, there's no angular momentum barrier. Now, of course, or sometimes known as the centrifugal barrier. Centrifugal barrier. Now, why does that make sense? That if the particle has more angular momentum, then there is this repulsive potential which keeps it away from the origin. Well, you can look at this picture of the orbits. If the particle has no angular momentum, then it's going to go streaming right to the origin. If it has angular momentum, well then it has a maximum distance it has to stay away from the origin in order to keep that angular momentum. So it's effectively like there's a barrier that keeps it away from the origin. All right? Well, let's just let's just say a couple of words. I guess we'll pick this up after Thanksgiving about the quantum mechanics. So let's look at the same problem that we were just looking at, motion in 3D in the potential. So my Hamiltonian in this case is p squared over 2m plus V of R. Okay? Again, I can break up my total kinetic energy in terms of exactly the same as before. Radial kinetic energy and angular kinetic energy. Okay? Where it's a little bit more tricky because piece of R here is the component along E sub R, which is X over R divided into P. That's a radial component. But these don't commute, so you have to write it in a symmetric order. This is the E sub R. All right, given that, well, what we see in this case is that there are the same symmetries. The fact that this is quantum mechanics doesn't change what symmetries there are. This is rotationally invariant. Which means the same things are conserved. Energy, magnitude of angular momentum, and any projection is conserved. So I can specify the energy eigenstate. Remember, the eigenvalue of energy alone doesn't specify the energy eigenstate if there are degeneracies. And if there are symmetries, there will be degeneracies. So I need more quantum numbers, more conserved quantities to specify which orbital, as opposed to orbit, I'm talking about. So they are what? What are three operators that specify these? We have N, L squared, and LZ. So if I specify simultaneous eigenfunctions of the Hamiltonian L squared and LZ, I specify the orbital.
So it's basically the NLM.
Exactly. So instead of orbits, we have orbitals, orbitals, right? Now, one last little picture I want to draw for you is, let's just look over here as exercise here. Let's look at the case of orbit where we had zero angular momentum. That's the case where the orbit's going through the origin. But if it's got to be rotationally symmetric, it can't be this or this or this. It's got to be a superposition of all of them, which is something that looks like a sphere. The S waves are spheres because they're rotation symmetric, but they represent probability amplitude always through the origin. Whereas, that's why they're spheres, because they go through the origin. Whereas the ones that have non-zero angular momentum always have zero at the origin, because you can't go through the origin if you have one. So there is mechanics in quantum mechanics. All right? All right. Well, we're going to just chug along with this next time. We'll continue to talk about this a little more. We'll get to spin something.